Good morning, class. I'm looking at my inbox and I'm getting some notifications that some students are logging into Zoom and instead of finding me on the live stream. So Thomas and Jackson, if anybody has their cell phone numbers, send them a text and let them know that we're here, not there. Okay, so I got 20 of you on here right now, and I got my chat window open. So as we talk, you got a question, leave it in the chat window, make a comment, and I'll see it and try to address it. So today, I want to talk about vectors and what they are and why they're important for physics. But before we get started, let's take a look at Sakai, because I've added a feature to Sakai that hopefully will help organize your classroom experience. You can call it that. All right, so here is Sakai, and I am open to our homepage. This is the student view, so this should look a lot like what you guys see. And what I've done is I've added a lessons tab to the menu here. And if you click the lessons, they'll be organized by week. And so if you click week 1, I've put some bulleted statements here which help guide you and remind you of what you should be focusing on that week. So, and there's some links in here, link to the syllabus, useful equation sheet. It's good to look at that and actually have a printout of it when you're doing your homework and studying. So what I'll do is I'll give you a subset of these equations when on the exam, when we take an exam. I put links to chapter 1, which should be a review for most of you. It's an introduction to science and scientific notation, but it should be reviewed, and make sure you are comfortable with that material. And then the first homework assignment comes from chapters 2 and 3 in the textbook. So that's where you should be reading from. So this course is a calculus-based course. And what does that mean? It means that calculus is a tool, but it's not used as much as algebra or trigonometry in the first semester. But some knowledge of calculus is important, especially derivatives the first semester. So some of you have had calculus, some of you are taking it right now, and what I've done is I created a video introduction to the derivative, and it's a good thing to watch if you don't know what a derivative is, you haven't learned it in calculus yet, you're starting right now, or you need a refresher. So there's a link to that right here. I've also posted a bunch of excuse me, slide decks. If you go into resources, there's a folder for slides and a folder for clicker questions. And I put some links here to some of those slide decks. Slide deck 1 is an introduction. Slide deck 2 is some slides dealing with vectors and one-dimensional kinematics. And so these may or may not be useful for you. Some people really like to look at PowerPoint slides. What are they? They're figures and equations taken from the textbook. So sort of textbook summarized in a visual way. There's some clicker questions. These are concept questions. On the exams, I'll always give you multiple choice questions. So I give you a link to a collection of conceptual questions relevant for this material. And then finally, there's a link to WebAssign. And there's a homework assignment posted there. Homework 1, 1D kinematics. See if I can log in. Spin. There we go. Okay, so there's a homework assignment here. It's due a week from today. And click Open Student View. What does it look like? So this is what WebAssign, make this a little smaller. So this is what WebAssign looks like. So when you log into WebAssign, there'll be this this home page where you can see the current and past assignments and the due dates, a summary of all that. And there's other stuff too, like a grade book. But when you click into the assignments, this is what a typical assignment will look like. So here you can see how many points it's worth. This is a two-part question. Each part's worth half a point. And you can see how many submissions you use. So one of the good things about WebAssign is that if you submit a wrong answer, it's not over. You can make corrections and submit again, and get full credit if you get it right on a subsequent submission. And so you're getting instant feedback. It's limited feedback. It's just telling you whether you're correct or not, and then you have to figure out why you're not correct if you're not correct. And that involves, you're reaching out to, potentially involves reaching out to me or another individual for help. All right. But this is what WebAssign looks like. Notice there's a link right here to the ebook. So you can go right to the section in the textbook that deals with this topic. In WebAssign, every student, if there's a number in red, that means every student is getting randomized values. So every student will get different numbers in this problem and thus have different answers. William asks, how many chances do we have to get it right? The default will be 5. You'll have 5 chances to get it right. That is, so you can't just guess until you get the right answer most of the time. But it should be plenty of tries to give you the opportunity to find the correct answer. There's another feature, it's called try another version of this problem. This is pretty cool. So you can practice another version of this problem. And you can't see that, but I click on that button and it opens up in another window. It's the exact same problem with different numbers, different randomized values. You can work on that problem, and those submissions on that alternate version don't count against your limited submissions. Okay. William, I will say the exception is if I give you multiple choice questions. I typically will give you just 2 tries on multiple choice questions, and that's because if there's 3 options and I give you 5 chances to get it right, what's the point? You can just guess until you get it right. All right. Okay, so we will do throughout the semester, we will actually do as a group WebAssign problems that are assigned to you on WebAssign. I'm not planning to do that today, but we'll see. Maybe we will have some time. And you do a couple, you get familiar with the interface and the system. And there's a few nuances like entering scientific notation. Some questions will ask you to enter answers in symbolic form, and there's this little pop-up window that does that. So I'll demonstrate that when that happens. Okay. All right. So I want to talk about vectors and what they are. So let me go to my whiteboard. All right. And make some space here. That's where we were last time. Okay. Well, actually, let's pick it up here for a second. Okay. So one thing, so we were talking about this concept of velocity last time, and one thing that if you're talking about how fast an object is moving in the world, there's a number associated with that. You know, I'm driving at 50 miles per hour, but there's also a direction associated with that, and that could be really important. I'm driving 50 miles per hour south. I'm driving 45 miles per hour east. And those two little bits of information are the essence of what a vector quantity is. So in physics, we think about the world in terms of physical quantities. We quantify the world using physical quantities. And in this class, there's two types of physical quantities. There's scalar quantities, which are just numbers, and vector quantities, which are quantities that have a magnitude, a size, which is represented by a number, but also a direction. Okay. So in the comments, let's see if you can think of any physical quantities, things that you would measure in the real world, which would be characterized as scalar quantities. They're just numbers. You would represent them as a number, but they don't have any directionality to them. All right, so if you can think of something, put it in the comments. I gave you one example of vector quantity, velocity, and there's others. We'll encounter momentum, force, acceleration, torque. You know, these things have a directionality to them. Tyler said speed. Yeah. So technically, if a physicist is being technical, when he uses the word speed, he means how fast something is going, ignoring direction. It's just the magnitude of velocity. So velocity is speed plus direction. Speed is just a number. Temperature, yes. William, temperature is a scalar quantity. Weight, gotta be careful. We'll see that, you know, if a physicist uses the word weight different than the word mass. And if you mean mass, yes, that is a scalar quantity. But weight is a vector quantity, because weight is another name for the force of gravity. All right. An object only has weight if there's gravity acting on it, but an object has mass even if it's alone in the distant far reaches of space. Length is a scalar quantity. That's right, Maddie. The vector quantity that has a magnitude equal to length is called displacement. You could say, I moved 5 meters. That's a distance, but I could also say, I moved 5 meters right, or I moved 5 meters left. So displacement has a direction associated with it. All right, good. You guys got this, I think. All right, so back to the whiteboard. Here we go. Okay. So you could say a scalar quantity is just a number. Okay. A vector quantity is a number plus a direction. Okay, and my pen is acting funky. All right, so we're going to focus on this concept for a while. So I got a question for you. and put an answer in the comments. The question is, if I were going to draw a picture to represent a vector quantity, what is the most natural symbol you can imagine to represent something that has both a size, a magnitude, and a direction? What's the most natural symbol imaginable? So if you think of something, put it in the comments. Let's see. Maddie, Maggie, arrow. That's right, an arrow. So let's say I have a quantity, and it's for the moment it doesn't matter what this is. Maybe it's a displacement. We'll call it A. Oh, sorry. Ugh. Okay. And I can, using a variable to represent a vector quantity, what you do is you usually put this little arrow on top of it. And you see that, you know, you're talking about a vector quantity. So I could say A is a displacement vector. Okay. And I could represent it using an arrow. Okay. And maybe it has a magnitude equal to 5 meters. All right, and then I can imagine there's another vector, B, which has a magnitude of 3 meters. And then I said there's a third vector, C, which equals A plus B. Okay. And I said, what is that? What is that sum? What is that sum? And so what I'm writing down here is a mathematical expression. It looks like algebra, but we gotta be careful. The answer is not 8. It could potentially be 8, but it's not always going to be 8. You know, like 5 plus 3, that's 8, right? Not when you're doing vector addition. When you're doing vector operations, things are more complicated. And the reason is because of that direction aspect, all right? So, it's a little smaller up here. So one way you could add these vectors together, graphically, if you're adding vectors together, it's like adding arrows together in a method that's called tip to tail, right? So one way I could add these vectors together is, well, maybe they both point in the same direction. So A and B both point in the same direction. So C would look like this. All right? So we call C a resultant. Okay. It's the sum of two vectors. So graphically, the way you add vectors is tip to tail, just like I've drawn it there. But maybe B points in the opposite direction. Maybe you have something like this, where A points like this, but then B is coming back the way you came. In this case, C would look something like that. Sorry, let's try that again. Okay. What I'm doing here is I'm drawing, in the first case, where A and B both point in the same direction, we say A and B are parallel. They point in the same direction. And in that case, you're going to get a maximum answer for the magnitude of the sum. 5 plus 3 moving in the same direction is 8. In the second example, I'm showing you anti-parallel, opposite direction. So you go 5 meters one direction and then come back 3 meters in the opposite direction. What's your total displacement? 5 minus 3, or 2 meters. Okay, so so you can actually answer this first question now in the homework. If I have these two vectors a and b and I add them together, a is 16 and b is 3, what's the maximum or the largest value they could be? It'd be when they're parallel and they add together, the magnitudes add together to 19. What's the smallest value you could get for the magnitude of the resultant? It would be 16 minus 3, which would be 13. And I got it right, green check marks. Okay, so all right, so let's think about, in this case, in both of these cases here, down here, what I'm doing is I'm adding vectors in one dimension, all right, and that's where we're going to start. Okay, so for adding vectors in one dimension, the most natural way to represent direction, there's only two directions, right? If you're in one dimension, there's only two directions, left, right, if your axis is left and right, or up, down, if your axis is up and down. And so in the comments, mathematically, what's the most convenient way to represent direction? Think about, here's a big hint, a number line. A number line, like the x-axis or the y-axis on a graph. What's the easiest way to represent the direction that you move along that axis? Mathematically, symbol. If you think you have an answer, put it in the comments. So you could go that way, or you could go this way. Positive or negative numbers? Yes, Holly, you're right. So in 1D, we will do, let's go this way a little bit. Direction. One of the things I love about this digital whiteboard is it's like infinite size. I never have to erase. Direction is positive or negative. And so one thing I want to tell you guys is there's an aspect of subjectivity here. Your positive may be someone else's negative. And you say, well, that doesn't make any sense. Positive on an x-axis, positive is always to the right, right, and the negative axis is always to the left. And I just realized that my camera's flipped, so that's why I got confused. But that's just a convention, You might be unconventional, and you might say, I want to call down positive and up negative. You can do that as long as you're consistent. So you define what you mean by positive and negative direction. Excuse me. So William, does that mean if they aren't parallel or opposing, do we have to do trigonometry to determine totals? Yes. So we're getting there. We're getting there, William. So we'll come back to, we'll come back to the 2D case in a little bit. But if we're talking about, the 1D case here, and I say positive A looks like that, then negative A is just going to be flipped. Here's something else. Oh, not B. I don't have B's here. I have A's. If I have 2 times A, what do you think that's going to look like? The same direction as A, but twice as long. All right. So graphically, that's how we can represent it. If I did minus 3A, we know it's not going to point to the right but the left, and it's going to be 3 times as long. All right, so yeah, now let's we'll take a look at the 2D case. So for the first problem set on WebAssign, you're going to be doing vector math involving 1 and 2-dimensional vectors. But when it comes to the actual physics problems, you're going to be considering physics problems that are in 1 dimension. Makes it a little simpler to start out. Let's see here. So let's go down here. And let's talk about the 2-dimensional case. All right. So let's set up a situation we can think about here. Let's say we have a vector. Let's use our colors because it's fun. We have vector A, which points up and to the right, and we have vector B, which points up and to the left. Okay, so I have two vector quantities that look like this. So maybe you're like, well, what could that possibly represent in the real world? Maybe they're displacements along compass bearings, where you're going, A is going northeast and B is going northwest. And you want to figure out, if you go a certain distance northeast and then turn and go a certain distance northwest, where are you relative to where you started? That's a problem that you would solve with this type of vector thinking. So if I have this and I say A is blue, A plus B equals some total displacement C, what does C look like? Well, I would have A, put A down, and then B and C connects where I started to where I ended. So it looks something like that. Okay, so C is the resultant of adding A and B in 2 dimensions. And the graphical way of doing that is the same. Tip the tail. All right, tip the tail. And then you connect where you started to where you ended. So what we're doing here is very qualitative in nature, if that makes sense. We're drawing pictures. I could turn my pictures into quantitatively useful things if I defined a scale and I said, okay, my vectors represent displacement, and a displacement of 1 meter is 1 centimeter on the page. And then I used a ruler to draw my vectors really carefully, and the vectors have direction, so I used a compass to get the direction just right, and then I measured the resultant using instruments. I could do that, but as William pointed out earlier, looking ahead, it's much more quantitatively useful to add vectors in 2 dimensions using tools from trigonometry. Trigonometry is geometry involving triangles. All right, and let's another way to think about this is it's easier to take something that's in 2 dimensions and break it into parts, 1-dimensional parts, and we call those parts components. And so for our 2 dimensions are x and y, we'll have an x and a y component. Okay. So let's take a look at how that's done. So let's just take a look at A. Sorry, my power cord is stuck on something. Okay. So I'll redraw A down here, but I'll draw it a little bigger. Okay, I'm zooming in a little bit. Okay. And so one way I could represent A is if I imagine there's an axis here. Well, I might as well draw them a little bit thicker. Okay. I have an x-axis and a y-axis. One way I could specify A is by saying A has a certain length, a magnitude, and then it has a certain direction, theta, relative to the x-axis. And that's the convention. The convention is direction is always counterclockwise from the positive x-axis. But maybe you're unconventional, and maybe your definition of direction is something like that, counterclockwise. All right. So that's one way you could do that. Holly, in the 2D case, do you also have to find a minimum and maximum value for C? So only if the question is, you have two vectors, what's the minimum and maximum value you could possibly get if you added those together. But usually, okay, so usually when you're actually doing a problem and you know something about a vector quantity, displacement, velocity, force, you know how strong that vector is or how big that vector is magnitude-wise, and you also know its direction. Or there's something else about the problem that constrains the direction. So if one way to think about this is if you know the magnitude and the direction of a vector, you know everything. Okay, there's no more uncertainty about that vector quantity. So you know what its magnitude is, you know its direction. So usually we don't think of vectors as having a maximum or minimum value. They have a value. Not sure if that is helpful, Holly. I think, you know, once you do a couple examples, you'll see how this works. But one thing you can do is, so one thing you can do is you can say, all right, A, let me assign a number here. So let's say A has a length of 10 meters. Okay. So one way you could specify this vector A completely is you could say A equals 10 meters at, let's say this is 45 degrees. At 45 degrees. Okay. And I drew a picture so I know what 45 degrees is relative to the x-axis. All right. But there's another way I could specify A. I could say, well, A could be thought of, sorry, I'm trying to erase some stuff here. I'm going to make a little space here. So another way I could think about A is the sum of a vector. Oh, I'm not doing. Hold on. Make it a little bigger. A is the sum of a vector that points in that direction and a vector that points in this direction. Okay, so using the tip to tail way of thinking, A is the sum of these two components, and one of them points just along the x-axis and the other one points just along the y-axis. So what we've done here is we've decomposed A into an x component, call it A sub x, and a y component, A sub y. All right, so just like before where we said C equals A plus B, here we can say A equals AX plus AY. All right, so AX and AY are the one-dimensional components that when you add them together give you the whole thing. All right, say that one more time. A, X, and AY are the one-dimensional components, just like A and B earlier. And when you add them together, give you the whole thing, which was C earlier, but now it's A. All right. So another way, these are two equivalent ways of specifying a vector quantity A. Another way you can do this is you can define, so since these are one-dimensional things, let's go right here, we have something called unit vectors. And unit means one, vector means are quantities that have magnitude and direction. So unit vectors are vectors that have magnitude 1, but we're going to have a thing, draw axes here. So we have a unit vector called I hat, which is the unit vector of magnitude 1 that points along the x-axis, and we have a unit vector j hat, which has magnitude 1 and points in the positive y-axis. So another way to think about these things, ax and ay, is their magnitudes multiplied by the unit vectors. The unit vectors give direction to the quantities, and the numbers ax and ay give the magnitudes to the quantities. So how we would usually write this is a equals the magnitude of ax, how long it is, times the unit vector I hat plus the magnitude of the y component j hat. Okay, and you'll see why this is convenient in a little bit. All right, you'll see why this is convenient. And there's also, it's not here, but we could also add a third dimension, a z dimension, and in that case the unit vector is called k hat. So we have I, j, and k hat. You might, if you take engineering classes, you will encounter this way of thinking in terms of unit vectors, vectors that have magnitude 1 and direction along the principal axes of this Cartesian space. And but for whatever reason in engineering texts, they don't call them I hat, j hat, and k hat. They'll call them x hat, y hat, and z hat, which kind of makes more sense because we're dealing with x, y, and z. But physicists have this convention of i's, j's, and k's. All right. Okay. So let me look at. All right. Okay. So how would you? Here's a question for the comments. All right. So the question is, how would you determine? Let's say that I told you A has a magnitude 10 meters at a direction of 45 degrees. How would you find AX and AY with that information? You know A is 10 meters and it's pointing 45 degrees above the positive x-axis. How would you find AX and AY from that knowledge? All right, I see. So what I'm getting in the comments are suggestions of using different kinds of trigonometry, the geometry of triangles. And so I should be able, we're going to actually restrict ourselves to the special case. You know, if you look at this, here I'll draw it in rainbow colors. Look at this, okay? So those components, I just gave it away. AX and AY and A, the total. What kind of a triangle is that? Put it in the comments. I don't see it there yet. This is a special kind of triangle. Right triangle, that's right. Yeah, Williams got it. It's a right. Who's PFH? PFH. Sullivan Epic. Right. Good. So it's a right triangle. And what does that mean? Right triangle means that the angle between the two sides is 90 degrees. And of course it is. It's 90 degrees because we're talking about the angle that two component vectors make when those components point along the principal axes of the two-dimensional Cartesian coordinate system, x and y. X-axis and y-axis are 90 degrees. Okay? So, all right. So how do you do this? We have the trigonometry of right triangles. Okay, and let's use the same notation, but I'm in this case we're just interested in the magnitude of these sides. Okay, so I got AX, AY, A, and there's an angle. Okay, so another way to think about this is when you're when you're dealing with right triangles, you position yourself, you reference yourself, you reference the sides of the triangles relative to the angle that you know, not the right angle, but the other angle you know. So, there's, ooh, that was weird. So we got this right triangle, and then we know this angle theta that's over here. So relative to that angle, AY is opposite, AX is adjacent, and A is the hypotenuse. And the hypotenuse is the side that's opposite the 90-degree angle, okay? And so in trigonometry, we have these three useful functions, sine, cosine, and tangent. The sine of an angle, theta, is opposite, I'll abbreviate here, over hypotenuse. Cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. Okay, so these are actually appreciate this. These are actually the definitions of these functions, and these are called these are called. There's a special kind of a function called transcendental functions. But these are the definitions of what these functions are. They're defined. The sine, the cosine, the tangent of an angle in a right triangle are defined as the ratio of sides. All right. So to translate opposite, adjacent, and hypotenuse to AX, AY, and A, what we have here is oh, that's weird. Cosine of the angle theta is AX over A. The sine of this angle theta equals AY over A. And the tangent of theta equals AY over AX. And if you look at that, you see that tangent is the same as sine over cosine. And so if you wanted to find AX, you could say, well, I'll just rearrange this first equation. AX equals A times the cosine of the angle. AY, use the second equation, equals A sine of the angle. Okay. And then somebody mentioned the Pythagorean theorem. Yeah, that's useful too because that links all the sides together. When you have a right triangle, the sum of the squares of the sides is equal to the square of the hypotenuse. And you can convince yourself that that formula right there is the same as, I don't know, maybe you guys remember this from trigonometry. The sine of an angle squared plus the cosine of an angle squared equals 1. All right, they're the same. You can make some substitutions and rearrange and go from one to the other. All right, so you know, this is hopefully review for you guys, but maybe it's not for all of you. But it's not that hard. You know, you just got to embrace the idea that these are functions that are defined as the sides, the ratios of sides of right triangles. Okay, and then you have to memorize them. Well, you have to. I guess you don't have to memorize them. In fact, I put these on the equation sheet when you look at them. But let me put that a different way. If you do things right this semester, you will memorize them because you'll use them so much that they become second nature. All right. All right. So maybe let's see. We're almost out of time. All right, so we'll end there today, and on Friday we're going to we'll start out. We're going to meet like this again on Friday, and my goal is next Friday we can start meeting in person and have a recitation session in person in the physics lab. And but Friday, let's start out on Friday by looking at one of the problems that I assigned. And then we're going to switch gears and start talking about the connection between position, velocity, and acceleration, okay, and see how all those things are tied together. All right. So let me see. Anybody have any questions before we go in the comments? All right, so I'll say one more thing before we go. If you have any suggestions or comments about how these live streams are going and how to make them better, what's working, what's not working, let me know. Just send me an email, all right? And it'll get better. So I will see you guys on Friday then. All right. So have a nice day.